So we left off. I don't know if any of you were watching the video recording, but my mic died 30 minutes in. I had told you guys on the first day I can't. It's not an online class, so I can't assume liability in case something like this happens. But I am sorry that it happened. So I know a lot of yesterday's video, if you ever try to go back and watch it, is just going to be a lot of me pointing and twirling and moving around and stuff. But we worked on this worksheet, applying charges. Now, I think I didn't give great instructions in class or on there, but what I wanted you to do is fill in what charge are you expecting along each row, what atom are you analyzing along each thing. I want you guys just to be thoughtful and reflective of that. So +1, neutral, and -1. And I wanted to use this example of two of our carbons as proof of molecular geometry, proof of electron pairs. I want to point out we're not doing molecules just yet. That whole table doesn't need to be bonded to anything in particular. So all of those bonds just ended. There could be hydrogens in places, carbons, oxygens in places. It was just for you guys to get familiar with bonding patterns. I believe that if you memorize that table, no, better yet, familiarize yourself with that table of bonding patterns, you will never miss a formal charge on any structure all semester. So how do you do that? Print off something like this, or just draw it yourself, and try and repeat all of the bonding structures and their charges. See which ones you remember, see which ones you forget. Get familiar with them. This morning in my OChem 2 class, they were doing a lot of drawing structures, and I probably pointed out a dozen times or so missing charges, because they're simple things to forget, but the more you familiarize yourself with those bonding patterns, the easier it is to see those charges. It's how I'm able to look at something at a glance and know whether it's missing a charge or not. So we mentioned here that we have a linear geometry around this carbon. And to have a linear geometry means that the atom is sp hybridized. I'm going to write that a little bit differently. So we talked about free atoms yesterday. These atoms that are forged in the heart of a star, that are not bonded to other things. These atoms whose electrons are only interacting with themselves. And for hydrogen, we really only deal with the 1s orbital. But for things like carbon, we have to deal with the 2s and the 2p orbitals. These are the orbitals of the free atom. But they're not arranged very well to be useful in bonding. Because if we use these atoms, which for the most part are just perpendicular to each other, then the only angles that we can bond with other atoms at are 90-degree angles. And that means that these other atoms are going to be coming in very close to each other with their own type of repulsion. Think about those magnets you were holding on the first day and the repulsive force that you felt. Those atoms want to repel as far away as they can. So in order to get something that has linear geometry instead of this 90-degree geometry, I need a new orbital. I need an orbital that is not s and is not p, but has features of s and features of p. Now, we could have named these new orbitals anything. We could have named them Frank. We could have called them linear orbitals. We could have called them anything we wanted. But sp, in my opinion, is a great description because it tells you exactly the building blocks of it. You take an s orbital, and you take a p orbital, and you take their mathematical equations, and you sum them together. Where they're in phase, constructive interference happens. The wave gets bigger. Where they're out of phase, destructive interference happens. But the thing is, if I take two orbitals and I combine them, I need to create two orbitals. Two orbitals in, two orbitals out. But these two orbitals are now both combinations of the s and p. So what we get is one big lobe and one small lobe out of phase. It's like 50% s character. It's very round, but it's also 50% p character. It has the two lobes. And that's just one orbital, and then the other orbital, we typically draw it as just facing the other direction. I've drawn them separate from each other, but I do want to point out that the nucleus would sit at the same spot. So in all reality, these orbitals are overlapped with each other because of where the nucleus sits, exactly for the same reason that the s and the p orbitals overlap with each other because of where the orbital sits. Now here's a really cool math feature that I like. We've only taken one p orbital, and that p orbital has a specific orientation, an x orientation, a y orientation, a z orientation. And when I hybridize it with s, which is just spherical, I maintain just one orientation. My p orbital was vertical. My sp orbitals are vertical. They maintain only the orientation that they had from the p orbitals. Align, linear. So one thing that we correlate sp carbons with is having two electron regions. And I encourage you to think of it like this. If I can count the electron regions, then I can count from s into p and figure out my hybridization. I have a region on the left that is bonding, a region on the right that is bonding, 1, 2, sp. The hybridization of the atom is sp because it has those two electron regions. What about the other orbitals? The p orbitals that do not get hybridized are still there. Since I took this py, if you will, because it's vertical, then this atom has my brand new sp orbitals. It also has the py orbital that was there, and it has the pz orbital that is going forward and backwards. Clear as day, right? Clear as mud. All of those orbitals overlap in some way, shape, or form. They take up a lot of space. But when I'm sp hybridized, I have two, what we typically will say here is we have two sigma bonding regions. And we have two pi bonding regions. If they're not pi bonding, then it's just an empty p orbital. But either way, that p refers to pi, and sigma refers to often some type of hybridization. It is a little hard to present because it's not always pi bonding. It can just be an empty p orbital. But I don't want to call it a pi region because it almost always is a pi bonding region. So if I only have two electron regions, I can't have any more electrons on this carbon. There can't be lone pairs here. So that's 4 valence electrons minus the 3 bonding regions, proof that that carbon had a positive charge. In my next atom, the geometry looks bent. And although it's hard to say, we really can say that it's bent 120, 120-degree angle between those bonding regions, which means that I have a trigonal planar electron geometry. Trigonal planar is what I want to point out there. Rather than talking about its molecular geometry, I'm interested in the fact that it has a trigonal planar electron geometry. Well, that must imply the presence of another electron region that is repelling them. And that electron region would have a lone pair in it. By having a lone pair, I've got 4 valence electrons minus 2 dots, 3 lines. 4 minus 5 is minus 1, so I've got a negatively charged carbon. How many electron regions? 1, 2, 3, hybridization, sp2. That is an sp2 hybridized carbon. 3 electron regions. How many of those regions could we consider to be useful for sigma bonding? Well, each region could be useful for sigma bonding once. Here I had 2 regions, so I could do 2 sigma bondings. Here I've got 3 regions, so I could do 3 sigma bondings. Yes, this is where I'm making it confusing. The lone pair is not bonding, but it could be used for bonding, and that would be a sigma bond. So we could call it a sigma region if you don't want to call it a bonding region. Why did I say 3 sigma sigma? Sorry. Well, in case you didn't know how to spell sigma, which means that it only has the capacity for 1 pi bond. So let's take a look again from our free atom. What happens when I take S, but this time with 2 p orbitals? If I have 3 orbitals coming in, then I need to get 3 orbitals going out. Okay, what I'm doing here is taking py and px. I could have taken pz, doesn't really matter. I'm just taking 2 p orbitals. And I'm also taking that s orbital. It's kind of hard to see it because it all overlaps with itself. And as I combine the mathematical equations, I get 3 new orbitals with new orientations. New size, shape, and orientation. Because I took px and py, my new orbitals are not limited to just one axis. They're now able to be displayed across a plane. By having px and py, I've created planar geometry. And because I'm looking to minimize electron repulsion, I'm looking for these groups to be as far away from each other as possible so that their repulsion is minimized. They'll take on this trigonal geometry. They'll spread out into 180 degrees. Earlier, I drew what happens with the sp orbitals and then the 2 remaining p orbitals. I'm going to try to do that again here, but I'm going to draw these new orbitals flat. I'm going to draw them. Here's one going this way. Another is going out of the plane of the board, and then one is coming out of the plane of the board towards us. So what I'm trying to have you see is that we're looking at these 3 orbitals centered on the nucleus, but we're looking at them side on. Remember that this creates a plane like a piece of paper, and we're looking at that plane. We're looking at the piece of paper on its side. I want to show you where the missing p orbital is, because remember there is an unhybridized p orbital, and that p orbital runs perpendicular to these 3 orbitals, to this new plane. sp2 is planar, and that pi region, that one remaining p orbital, is perpendicular to that plane. It's a little more confusing when we look at sp hybridized because it's got more going on, but this, easier to interpret. We've got our planar region with our sp2 orbitals, and we've got that perpendicular pi region. Okay, so just by looking at the electron regions, doesn't matter what it's bonded to, just by looking at the electron regions, we can determine hybridization and geometry. And this is not unique to carbon. This will transfer to nitrogen and oxygen as well. We can predict hybridization of any of these atoms just by looking at their electron regions. The last thing for us to consider then would be a tetrahedral carbon. Do you guys know what tetrahedral means? Four faces. Yeah, four sides. What part of that name indicates four? Did you guys know that tetra means four? When did you learn that? Gen Chem 1? The first time you heard tetra? Did you know that it's related to the game Tetris? Because all of the blocks in Tetris are four-piece blocks. That's why Tetris has the name Tetris. I learned that literally a year ago. Okay, in order to become tetrahedral, there must be, or this atom must be sp3 hybridized. It must have 4 electron regions. I hope that you've been recognizing that the number of hybridized orbitals gives us sigma regions. The number of unhybridized p orbitals gives us pi regions. P and pi is an intentional alliteration. The fact that they start with the same letter is on purpose. P and pi, the number of p orbitals is related to the number of pi regions. 1 p orbital in sp2, 1 pi region.
So you're saying that pi bonding regions are dependent or counted by the number of unhybridized p regions. So like in the tetrahedral, you should expect 4 sigma regions and 0.
Perfect. Well said. Because the tetrahedral needs all 3 p orbitals, there are no unhybridized p orbitals. So there cannot be any pi bonding. There cannot be any pi characteristic. This will have 4 sigma regions and 0 pi regions. Did I make this confusing enough? I'm just upset that I'm calling this pi bonding despite the fact that this carbon actually has an empty p orbital. It's not both bonding, but one of them is a pi region. Gavin?
You're saying if we don't use the p, then it becomes a pi bond, essentially.
Yes, if p is not used in a hybridization, then it stays unhybridized and it can be used for pi bonding. Exactly. Pi bonds require p orbitals. That's a lie. D orbitals can do pi bonding too, but we're not going to have to deal with d orbitals yet. Maybe. Okay. Those are our hybridizations. sp, sp2, sp3. The same thing that you do to analyze them on carbons, you do for nitrogens and you do for oxygens. Hydrogens don't hybridize. Why?
They have 1 bond.
They've only got 1 orbital, so they can't even combine orbitals because they've only got 1. And they just want to make that 1 bond. They're very close to being full. Elvira?
Oh, I just wanted you to draw the little
Oh, yeah.
bubbles that you had drawn for the tetrahedral.
I'll try.
That's helpful.
It gets really hard. So first of all, if we're going to sum them up like this, we're taking 4 orbitals in, and we're going to get 4 orbitals out. I didn't do a great job managing my space over here, so I'm going to try to fit it in here. I'll do this one in green so it stands out a little bit more. This requires that we take the py, the px, the pz, and the s orbital, which are all localized over the nucleus. And we take all of their mathematical equations at once, and we pump out 4 new orbitals that minimize electron repulsion. That's the whole point of hybridization. Do you see that? These groups don't want to be near each other because they are all magnetically repelling. So to minimize that repulsion, we get new orbitals, but we are limited to the orbitals that were available to us. So we are just reconstituting them. So 4 orbitals in means 4 orbitals out, but these orbitals, they make up the shape of a tetrahedral. They point in these 4 faces. So what I'm trying to show here is something like this. A wedged group comes towards you. And a dashed group goes away. So you can see how drawing those orbitals, trying to show that one of them is coming towards you and one of them is going away from you, it's actually quite hard to do. It doesn't look pretty at all. That is what it is supposed to look like. It's hard to do 3 dimensions in 2. This, I think, is a bit easy. Like, that's not hard to draw. It's not hard to sketch. It's hard to sketch orbitals that are, because if this one is really coming towards you, then that lobe, that white, that unshaded lobe, is going to look bigger because it's coming towards you. And if this one's going away from you, that unshaded lobe should look smaller because it's going away from you. And the shaded lobe should look bigger because it's closer to you. I have tried doing something with Desmos. I think maybe I'll try demonstrating it with you guys. My intention was actually to use this in the fall with my general chemistry students. Sorry. You guys know Desmos, the online graphing calculator? Oh shoot, I logged in with the wrong account. I don't know what account I had logged in then. So Desmos allows you to do 3D graphing as well. Oh no, all of my graphs are gone. I don't know what happened to them. Maybe it's with my school email. And I actually tried to work with AI to do this. So AI helped me come up with the mathematical equations that I could plug in here. I'm going to try and get this on the camera as well. So you can see that equation in the top left, yeah? That equation in the top left helps us draw a circle with this size and shape. Okay, so there's the mathematical equation of a sphere. And we are saying that that mathematical equation can help describe the behavior of some electrons. Here is the mathematical equation of a p orbital. Notice how it has those 2 different lobes. I'm actually using 2 different equations where I'm saying it's equal to z or it's equal to negative z. Remember that I said the shading just tells us whether it's positive or negative in front of the mathematical equation. That's what we're getting at there. And this is what we would see representative of pi bonding. Those p orbitals overlap with each other side to side so that they're in phase with each other. What is it doing? And it's that constructive interference that would allow electrons to be in both regions. So that's how a pi bond forms. 2 p orbitals sit on top of each other. Now here is my attempt to show how hybridization of s and p works. So here's my s orbital, here's my p orbital. You can see they're getting cut off a little bit in my graph. I've got constructive or overlap on the top, destructive on the bottom. And when I put that all together, I get a bloated top and a more constricted bottom. I'm just mathematically combining these regions. Here is what the tetrahedral looks like. There's that three-dimensional geometry, and you can see a little bit more clearly how there's actually two different planes. What I have right now has set blue and green into one plane. That would be like these two green lines that I drew before. They're in one plane. Red and gray are the other plane. Where's the gray? It's behind it. It's eclipsed right now. You can't see it because they're in plane with each other. That is not very useful if we're going to draw it like this wedge and dash, because I wouldn't see the dash ever. So the way that we actually draw it is just offset a little bit. So I can see what's coming forward and I can see what's going backwards. And technically now the green and the blue are not exactly in plane, but we just tweak it a little bit so that we can visually represent everything. This might not seem important, but I don't know what just happened. The physics of this is incredibly important. The fact that it points in 3 dimensions is quite important. I guess it's done. It didn't want to keep going anymore. That was all I had for it anyways. I want to point out ways that I don't want you to draw it, although I understand at first learning the difference might not make a lot of sense. We've got the wedge and dash. Those are a set of planes. We've got the 2 flat lines. Those are a set of planes. What I do not want to see is something like this. The way that I'll describe that is the wedge and dash bisect the 2 flat lines, the 2 things that are in plane. That is not what we saw on there. What we saw is that out of this vertex from the flat lines, the wedge and the dash group both come out of it. You should use that vertex of the flat line to draw the wedge and dash outward. You should not bisect like this. This will become very, very important later in the semester. There are certain problems that if you draw a structure like this, you physically cannot get the correct answer because you are misinterpreting physics. This is like trying to draw the Eiffel Tower, but your Eiffel Tower looks like this, and there's the little thing at the top. No one's going to understand how you get to the top of the Eiffel Tower if you show them a representation like that. That's what you're saying here. That's how little sense it makes. And I know that I'm just saying that at you, but we'll practice it and we'll see how it's true. Okay, Gavin.
With these like electron planes or orbitals, like we've never actually seen it. It's just been determined mathematically, like what it's supposed to be.
Oh, well, okay, you want to get me on a tangent. That worked. I wish this worked because I have a YouTube video for you. Do you guys know the channel Veritasium? I love Veritasium. They are one of my favorite science educators on YouTube. They released a video. This is a video of light travel. Sorry. They released a video 4 months ago on, it's called What Happens If We Keep Slowing Down. It's going to take a while to turn back on. Maybe I'll show it if this works. They are essentially using pulses of light to excite electrons inside of a molecule and the frequency of the light used can target specific electrons in the molecule. Then they send a second pulse of light afterwards, which interacts with the molecule and is reflected down at a specific energy, telling us how electrons are moving, how electrons are behaving in the structure. So one pulse to excite and one pulse to kind of scout out the energy environment of the molecule. And they're able to send these pulses at about 30 femtosecond spaces. A femtosecond is times 10 to the negative 15. To live through, what did they say? No, it's not a femtosecond, it's an attosecond. So I think maybe I have, I'm not sure, it might be to the negative 18. There are, it's really hard to say it, and he said it well. To live through enough attoseconds to fill 1 second would be to live through enough seconds to live through the life of the universe. The universe is 13.8 billion years old, and to live through that entire time would be the same gap from 1 attosecond to 1 second. It's an incredibly small scale. It's crazy to think about. And this is the scale that they're pulsing electrons, or measuring electrons at. By doing this, they can visualize the energy of the electron, which is described by a mathematical equation. So they can take the energy and back calculate what the orbital would look like for the electron to be at that energy. So we are learning how to probe molecular orbitals. We're learning how to probe what orbital densities actually look like to see if they agree with our simulations.
That's cool.
But you can't really see, certainly not with visible light, you can't see an orbital because an orbital doesn't exist. It's the electron that exists. But also, do electrons exist? They're like both particles and waves. Quite confusing. There's not an easy answer there. Okay, I'm going to maybe come back to this later, but I think for now we move on. So I want to take us from this idea of hybridization into how hybridization plays a role in the molecule. So I want you guys to draw out the Lewis structures for the molecules on the back side of the page: HCN, CH2O, CH3, COH. If you don't want to do SOCl2, I think I'd actually rather that you do H2SO4. So I'm going to put that one on the board. Why don't you take about 5 minutes and try to draw the Lewis structures for those molecules.
I think it would be, carbon would be the central atom, with one going to hydrogen and three going to nitrogen. Because nitrogen wants three bonds.
Yes. But it would have a lone pair, one lone pair, because carbon can only take the three.
It wouldn't have any lone pair, because carbon would have all four bonds, three to nitrogen and one to hydrogen.
Yes, but nitrogen would have one pair.
Yeah.
Yeah, okay.
Yeah, but it's not the central atom, so it's not affecting the shape.
Yes.
It'd be linear.
I agree. And then I drew it as like a double bond carbon oxygen from carbon at angle to try and yeah, the planar.
You were right.
Oh, I was right.
You were right.
Okay, I was just like thinking like morning break.
But there is something more we could add, which is the lone pair that nitrogen has.
Which is one.
Perfect.
Yeah.
Yep. Fun, huh?
It's all coming back.
Yeah, it's all remembering how to do this.
We're not going to do a lot of Lewis structures this semester. We're going to do bond line structures. But a Lewis structure, one of the Gen Chem rules would have been count your valence electrons. Make sure that you know exactly how many electrons are in the structure, no more, no less. Put the least electronegative in the middle, or the atom that is most willing to make the most bonds in the middle. And then single bond everything. And then put in all the lone pairs. And then make sure everything satisfies its octet.
Is this right?
No. Too many electrons, actually. And think about the charges that would have. It would be, it would have been a negatively charged carbon and a negatively charged oxygen.
Because I thought it all needed 8.
Sure, they do all need 8. But also, carbon is bringing 4, plus 2 from the hydrogens, plus 6 from the O's. So that's a total of 12. You had 14 electrons. So you can't just put in 8. You've got it, Delaney?
Whoa, almost. Then we get here though.
I know, that one is just to torture you guys. Good work, Kayla.
Hey, nice to meet you.
Nice to meet you
Sorry
too.
I wasn't in the first 2 days. I broke my toe before going to class. I dropped an iron.
You're kidding.
I was like straight out of Looney Tunes.
Whoa, I'm sorry to hear that.
It's okay.
Thanks for coming in.
It happens. That's life.
That is life. Off to a good start, Andrew.
Does that look okay?
Absolutely. That's perfect.
Yeah, this section's a little trickier.
Yeah, it's just like big.
Does that seem right?
No, it seems crazy.
Oh, dang.
I think what it is, you've got too many carbons.
Oh,
CH3,
you're right. Okay.
3.
Hold up, I don't know why I thought.
Oh no, I wouldn't have done all of that. Yeah,
Because there's 3 methyl groups.
there's 3 CH3s, yep.
There's that group,
And then they're all connected to a C.
so what it is I need to remove this guy.
Right.
That's what it's supposed to look
So carbon with 6 bonds, love that.
like. There we go.
Nice.
That's
Now,
kind of the structure.
think about the table we had just finished making. How many times did we see oxygen bonded? 4 times. Because that's what you had, yeah? You had a triple bond to O and then a single bond to H. How many times did we see O with 4 bonds?
That's a good question.
Here's our O.
0 times.
0 times. Oxygen does not bond 4 times. It doesn't have that capacity. Well, it's close, but I see 1 CH3, 2 CH3s, but here's a CH2 and here's a CH. And it doesn't have the OH. So what you need instead is to just change the position of where some of your groups are so that there are 3 CH3s all bonded to a central carbon.
Okay.
So does that mean with this drawing in particular, this would be so it'd be like.
No, because that means you didn't consider your lone pairs on the O.
There's 4.
Oh,
there's
that's
2
right,
lone
that's
pairs
right.
on oxygen.
That's right. It's a neutral oxygen, right?
So
Just like our table yesterday.
So which means that it needs to have.
Perfect.
It needs to have an pair here and a pair here.
Good. Now,
It would be 1, 2, 3, 4 sp3.
perfect.
Okay.
Yep.
Is this one correct? And then that'd have 3.
Perfect. Now draw in the lone pairs on the O, and you've nailed it. Great work. Not quite. H2SO4 is a funky molecule, and I learned how to draw it really early in Gen Chem. My professor really liked it. And I've learned that not everyone has ever seen the structure of H2SO4 drawn out completely, which is why I want you guys to try and play around with it. Too many bonds to carbon.
1, 2, 3. Oh,
Plus, that's a 3-bonded O, which we learned yesterday would be positive, right? And I don't think we're looking for a positive.
so
Good.
just be
Good. Great.
I'm kind of confused because would you just consider this just one region, or is it two regions because it's two lone pairs?
2 lone pairs, 2 regions.
Two regions.
You got it. This is great too. Great job. How you doing, Madison? Please, I'm supposed to. This is actually not a method I'm familiar with, but
I kept accidentally drawing lines because I was trying to like visualize it in my head
sure.
by drawing lines, and then I drew lines.
But it's good. It's okay to draw lines. It's okay to draw the dots, whatever works best for you.
Yeah.
We want to try and line things up so that they get their octet rules satisfied, right?
Yeah.
So we know H and C can form one bond because H can only form one bond. But that would mean carbon has one. So how many more bonds would carbon like to have? Think about our last page. When carbon is neutral, how many bonds does it like to have? Right. So carbon has 1, it wants 4, it needs 3 more. Where are those 3 going to go?
Somewhere.
They're going to go to the nitrogen. There's only one atom left.
Yeah, I guess that's true.
And nitrogen likes to make how many bonds? 3, and keeps a lone pair. You didn't draw your lone pairs on this document. Like this has a lone pair, lone pair, lone pair, 2 lone pairs, 2 lone pairs,
Yeah, I didn't
3,
catch that, yeah.
4. But if you use this as a guide, you can actually find the common bonding patterns that are in that table and use it to predict what your structure will look like.
Okay.
Okay, I found. Oh, well, now it's going to play an ad, so I'm not going to play it yet.
Yeah, but it can usually find.
Okay, I want to play this clip from what happens if you keep slowing down. Oh, I really hope it shows. Because it does a great job illustrating how crazy electrons are. Oh, man. Okay, great.
What that means exactly is debated.
Oh. Sorry. Double time. And it's not connecting the audio up here.
Electrons act like waves. No, they don't exactly. They act like particles. No, they don't exactly. We can write mathematical expressions and calculate what the thing is going to do without actually being able to picture it.
Do electrons exist?
How truthful do you want me to be?
Now, we still don't have a video or photo on.
Okay, that was Richard Feynman, a world-renowned physicist. Those of you that took Gen Chem here might have actually done Feynman notes. He is the designer of this like meta-cognitive approach. Think about what you're thinking about. Think about what you know. Think about what you don't know. And he said, electrons are waves. Well, no, they're not exactly. Electrons are particles. Well, no, they're not exactly. We can write mathematical equations. We can draw visualizations. That's what these orbitals are. Then over here at 2359. Okay, well, this is actually cool too. This is how they move electrons using magnets.
If you compare that to wavelengths, that is in the X-ray domain.
Now, that actually only gets you to stand at the far end of the accelerator.
Oh, I missed it.
Resulting isolate Moses curved lines.
Sorry. They take electrons and they shoot them through
push them in a direction
magnets.
perpendicular to both their velocity and the magnetic field lines, in accordance with the left-hand rule. So at one magnet pair, the electrons will curve clockwise, and at the next pair, counterclockwise, and so on. This causes the electrons to wiggle. Now, since electrons carry a charge, this wiggling motion causes them to emit electromagnetic radiation. And even though they oscillate at these millimeter wavelengths because of the magnet spacing, the wavelength of the resulting EM radiation is much smaller.
Crazy, right? Because they're not even particles, they're actually just waves. But they're not waves, they're particles.
As a couple hundred attoseconds.
That's 10 to the power of negative 18, an absurdly quick pulse. To put it another way, the attosecond is to the second what the second is to the age of the universe.
That was said much better than what I said. The attosecond is to the second what the second is to the age of the universe. And electrons operate in this like attosecond world. I have sometimes dabbled in the idea that maybe electrons could have a form of consciousness. We don't really understand consciousness. We don't really understand electrons. Who's to say electrons aren't conscious? If an electron were conscious, it would need to live through the age of the universe just to exist for 1 second. So if they were conscious, do you think we'd have any way of comprehending what that would feel like for them? Not at all. Much like other things that to them, the age of the universe feels like a second, they wouldn't be able to comprehend our experience of consciousness.
On the attosecond scale, you can see electrons.
What they do with all of this then is they shoot it at molecules.
The polarization state. We can change the duration of the pulse. So we sculpt these pulses, then we have them go co-propagating with the X-rays into our target. And so now our first laser pulse will create some non-equilibrium state in the molecule. We'll drive some dynamics, and then our X-ray pulse will probe it.
This attosecond X-ray pulse ejects an electron from the molecule after a time delay t. And by measuring the kinetic energy of that electron, you can study how the electron density of the molecule reacted to the trigger laser. So you get an attosecond snapshot, like a strobe, of how the molecule changed. Then you can get another sample of the same molecule, shoot it with a laser again, but this time increase the probe delay slightly to t plus delta t. This will tell you how the electron density changes a little later. And you can keep increasing this delay each time to get a sequence of snapshots of how that electron density evolves over time.
Isn't there a big assumption here that every time you do it, you're expecting a repeatable result?
Yes.
Okay. I was wrong. They don't emit light that they analyze. They emit an electron that they analyze. And based on the energy of that electron, they know the energy of let's just see that. I think it's still going. I don't know what happened. It might just look like a blip. Anyways, one way that you might have learned how to draw Lewis structures is to use the Lewis symbols. So hydrogen has 1 Lewis dot, carbon has 4, nitrogen has 5, and then try to get all of these dots together to form bonds. So I'm going to take H and C, I'm going to take C and N, and I'm actually going to take C and N multiple times so that all of them get a full outer shell. So this would be 1 bond, 1, 2, 3 bonds, a lone pair, and then we would draw this like this. This is not a process that I am really familiar with, and to be honest, I think it misleads the idea of how they form. Molecules don't form from these free atoms getting close to each other and then distributing their electrons. Almost every single molecule that you've ever interacted with formed by result of a chemical reaction where it already was bonded and now it's just bonded in different ways. So the way that I would solve this is actually to say, I've got my 3 atoms, and I know how many valence electrons I need to have. Even if I don't know how many valence electrons, I know what their stable bonding patterns should look like, because it's on that table on the other side. You see all of the possibilities for their bonding patterns. I know hydrogen can only make 1 bond. I know carbon wants to have 4 bonds. So where is it going to get the other 3? It's going to have to get the other 3 from nitrogen. And on that other table, when nitrogen had a triple bond, it also had 1 lone pair. So just by virtue of familiarization, we can design this. Let's do the same thing for CH2 O. Now, it might not be obvious to you where the hydrogens are bonded to, but we put the least electronegative in the middle, except for H. So C is going to be the one that bonds to all of these. Again, I know there has to be a single bond between everything. And I know that carbon wants to have 4 bonding regions. The only way it can get a 4th bonding region is if oxygen has a double bond. And now looking at that table, when oxygen has a double bond like this, it also has a lone pair. 2 lone pairs. So we can use that old process, or we can simply apply familiar bonding patterns. And we can actually build Lewis structures fairly quickly. But if you are not familiar with this being a neutral oxygen, then you need to take that table that we filled out, you need to draw it from scratch. Fill in all of the common bonding patterns with a positive charge, with a negative charge, until you can do it from memory. Get familiar with them, because by the time you're familiar with them, structures become a breeze. So what are you going to do this weekend? Redraw that table from scratch. Do it until you can do it by memory. Okay, this one's a bit more challenging. I've got this carbon that has an OH bonded to it, and then also 3 carbons that are each a part of a CH3. Oh, well, it wasn't actually that challenging. It's just tedious. It's a big structure. And then again, I see that O has 2 bonds, and when oxygen has 2 bonds, it also has 2 lone pairs. Great. Now, H2SO4, I noticed some of you were doing SOCl2, so I'll put that one up as well. H2SO4 trips a lot of people up. They're really not sure where the hydrogens should be. They're not sure where the oxygens should be. Sulfur is an odd structure in the periodic table because it has the capacity to take more than 8 electrons in its outer shell. Sulfur is fine with 8 electrons, but because sulfur has d orbitals, sulfur can take more than 8 electrons. So sulfur expands its octet here. It turns out that the hydrogens are bonded to 2 of the oxygens, and the other 2 oxygens are double bonded to the sulfur. In SOCl2, thionyl chloride, we see something a little bit similar. The chlorines like to have 1 bond, oxygen 2, and sulfur actually has 4 bonds and a lone pair. Use that formal charge equation, valence electrons minus dots plus bonds, and you'll find that sulfur is a formal charge neutral in both of these structures. The reason sulfur expands its octet, the reason it takes more than 8 electrons, is to become formally neutral. If sulfur followed the octet rule and had single bonds in H2SO4, it would mean the oxygens were negatively charged. There would be 2 negatively charged oxygens and a positive 2 on the sulfur. Because sulfur with just 4 bonds, 6 minus 4 is plus 2. If sulfur didn't have this lone pair, it would be plus 2. If sulfur didn't have this double bond, it would be plus 1. Sulfur expands its octet in order to have no formal charge. It minimizes formal charge by expanding its octet. All right, fun stuff, right? I am not so interested in you being as familiar with sulfur as you are with oxygen, nitrogen, and carbon. But I do want to talk about the bondings here. So which of these atoms has 1 pi bond? Or which of these molecules has only 1 pi bond? The CH2O. A pi bond comes in the multiple bonds. When you have a double bond or a triple bond, there is always a sigma bond, and that sigma bond is the overlap of hybridized orbitals. The pi bond is everything extra using the p orbitals. So I want to look at HCN, and describe the hybridizations, because then we can say what orbitals are needed to overlap to get that bond to form. So what is the hybridization of carbon in HCN? SP, exactly. In fact, another thing I forgot to mention, on that table where we did common bonding patterns and charges, you could go through at each of the atoms and try to figure out what would its hybridization be based on the electron regions. So carbon is SP. What is nitrogen? Also SP. What is hydrogen? Yeah, hydrogen only has that S. Valence bond theory, or VBT, says that bonds result from the overlap of orbitals. So a sigma bond comes from S with hybridized orbitals or hybridized orbitals with hybridized orbitals. S can never make a pi bond. So anytime an S orbital is overlapping, it's a sigma bond. But anytime hybridized orbitals overlap, we also call that a sigma bond. A pi bond results when a p orbital overlaps with p orbital, unhybridized p orbitals. So let's look at this bond on the left between H and C. Is it a sigma bond or a pi bond? Sigma. Why? Because it's hydrogen, and hydrogen will only make sigma bonds. And this sigma bond is the result of what orbitals overlapping?
S and S.
Not S and S.
S and pi.
Not S and pi. Pi is not a bond. Pi is not an orbital. P would be an orbital. But it's not S with P. S with the hybridized orbital. What's the hybridized orbital on that carbon? SP. So this is the result of S with SP. I don't always show that with a positive. I think a lot of times I show that with a dash. That sigma bond is the overlap of S with SP. Saray? We know that carbon and nitrogen have sp orbitals because they have 2 electron regions. And those 2 electron regions want to repel as much as possible, which would be 180. And to get a linear geometry like that, you need an sp hybridization. So we can use their bonding or their electron regions to infer their hybridization. Okay, there is a sigma bond between C and N. What orbitals overlap to give that sigma bond? Sigma bonds, sigma bond, sp and sp. The p and p overlap gives what type of bond? Pi. And how many pi bonds are here? There are 2. Remember, sp leaves 2 unhybridized p orbitals that can then be used for pi bonding. So there's 1 pi bond from p to p, and there's a second pi bond from p to p. Okay, how about this? What orbital does nitrogen's lone pair sit in? How can we describe nitrogen's lone pair? What energy would describe it? All of nitrogen's p orbitals are consumed. Its s doesn't exist anymore because its s was hybridized with one of its p's. Its p orbitals are all being used. It has 2 p orbitals. It's using them in pi bonds with carbon. It has no S. Huh? It doesn't, yeah, it floats in an orbital size and shape with what characteristic? Okay, let's think about it this way. Carbon, being sp hybridized, has 2 sp orbitals and 2 pi orbitals, or 2 p orbitals. One sp orbital bonds to hydrogen, one sp orbital bonds to nitrogen, the 2 p orbitals bond to nitrogen. Nitrogen has 2 sp orbitals. Nitrogen has 2 p orbitals. The 2 p orbitals bond to carbon. One sp orbital bonds to carbon. The only other place for the lone pair to sit is in the unused sp orbital. This is a non-bonding pair, so we're not going to call it sigma or pi, but that pair is still somewhere behaving a certain way with a size and shape and orientation described as sp. Okay. How about formaldehyde? What is the hybridization of carbon? Hybridization of oxygen. Good. Both are sp2. What bond do I have between C and H? Sigma resulting from? Not S overlapping with P. Not sp, because this carbon doesn't have sp orbitals. S with sp2. You see it now? Also, that is a superscript 2, almost as in squared. It's not a subscript 2, and it's not a coefficient 2 or something like that. That's just how we represent the orbital name. So carbon has 2 types of orbitals here. It has sp2 orbitals, and it has 1 p orbital. And it is the hybridized orbital creating the sigma bond. How about on the right? Same thing. Sigma resulting from S to sp2. How about between carbon and oxygen? Is there a sigma bond? Yes. Every bond has a sigma bond. Every bond has a sigma bond. sp2 to sp2, it's the hybridized orbitals from both atoms, and we know they're both sp2 hybridized. What constitutes the pi bond? The p to p. spp leaves one p orbital unhybridized, and that unhybridized p orbital on both of them will overlap to give us the pi bond. Why did HCN have a second pi bond? It had a triple bond. There were 2 sets of p's. This has 1 pi bond because it's only a double bond. There's only 1 set of p. What orbital holds the lone pairs? sp2. Oxygen's hybridized orbitals that are left over, remember it has 3 of them and only 1 is being used for bonding. Those hybridized orbitals are being used to hold the lone pairs. Gavin?
So can we assume that every bond after the first bond is a pi bond?
That's a beautiful way of saying it. That's exactly true. Every bond after the first bond is pi. Every bond has 1 sigma bond. No bond has more than 1 sigma bond. Every bond after sigma is pi. Beautiful way of saying it. All right, I don't want to redraw this beast, so can we just come, I'm going to draw it over here. Hybridization of every carbon is what? sp3. So let's just pick one of these CH bonds. What type of bond is it, sigma or pi? Sigma. It's the overlap of what orbitals? S and sp3. Perfect. What about our carbon to carbon bond, sigma or pi? Sigma. Overlap of what orbitals? Good, sp3 to sp3.
But there's still remaining
Do you see any double or triple bonds? I see no double or triple bonds. So every bond is a single bond, which means every bond is a sigma bond.
So is every first bond always a sigma bond?
Every bond is a sigma. Anything additional then is pi. Yep. Come back to it. What about the O to H bond, sigma or pi?
Sigma.
And the overlap of what orbitals? That oxygen is sp3 as well. If you don't draw the lone pairs, you might be convinced that the oxygen has 2 electron regions and would be sp. But that oxygen has 2 lone pairs, which means it has 4 electron regions, sp3. So this is S to sp3. Perfect. What about the C to O?
sp3, sigma, sp3 to sp3.
Perfect. You guys getting the hang of it? I'm just going to draw this one up here. It's the exact same thing. And what type of orbital holds the lone pairs? sp3 orbitals hold the lone pairs. sp3 atoms have what type of geometry? Great. Tetrahedral. Gavin.
So the type of hybridization will always be the type of orbital that the lone pairs are held in?
Good. Hybridization. Okay. No, once you get to OCHEM 2.
But for now.
Yep. In OCHEM 2, we actually see molecules where a lone pair sits in a p orbital instead of an sp2 orbital, and that actually allows it to do pi bonding, which it only does in the event where that pi bonding stabilizes the compound. So come on over to OCHEM 2 this fall, and I'll tell you more about that. But for your purposes this semester, yes, it is only the lone pairs are held in those hybridized orbitals.
So the reason that there's no pi bonds in compounds with only single bonds is because there's not an extra p floating around to match up to make the pi bond?
Yeah, if all of your atoms are sp3 hybridized, then all the p orbitals are gone.
Yeah.
You couldn't possibly get a p orbital to overlap. So I want to show some of what we just did. We took S with sp. We took S with sp2. Do you see the difference between S and sp and sp2? There's like hardly a difference, right? The size of the lobes change a little bit, but that's it. We took S with sp3. That just a little bigger. That's pretty much the same thing. That's the S to hybridized overlap. We also took sp to sp. That's the overlap that we're looking at. We took, we could take sp to sp2. We took sp2 to sp2. We could take sp to sp3. I'm like saying that these are different orbitals, but because their size and shape is just barely different in the lobes, they all look the same. You're just getting this overlap of the orbitals, which means that now the electrons can be in both of those regions. So the electrons are shared by the atoms.
Can you draw the pi bond?
Yes, so pi to pi, I actually demonstrated this on the Desmos earlier.
Yeah, okay, yeah. Oh, yeah.
They sit next to each other in phase, both on top and on bottom. And they're perpendicular to each other. Nope, sorry, they're parallel to each other. What that means, though, is that they're perpendicular to the sigma bond. So if this is their pi to pi overlap, then their sigma overlap is running perpendicular to that. It's beautiful. Now, I'm going to show you something that's even more beautiful, and we call it molecular orbital theory. Anybody that's learned MO theory, molecular orbital theory, before in general chemistry?
Sounds familiar.
Okay. We skip over it often here at SLIC. I don't know that any of our instructors teach it in Gen Chem. I mention it every now and then, but valence bond theory is useful for looking at Lewis structures and interpreting what we see about the molecule. molecular orbital theory is useful for explaining things. For instance, why bond? Why do these atoms prefer to come together to bond?
They're hungry for to complete their valence shells.
They want to complete their valence shells? Okay, prove it. I don't see it. I don't see how this reaches a lower energy state. I like that idea. They aim to be more stable. And that is the idea too, is that when they bond, they're in an energy well. Does this help depict that energy well by any means? Not really. So valence bond theory helps us with interpreting structure, but it doesn't help us interpret why. And molecular orbital theory helps us more with the why. We'll abbreviate molecular orbital theory as MO. And the name is exactly what's going on. The name tells you exactly what's going on. It's not atomic orbitals like P and P or SP and SP or S and SP. It's now orbitals that span multiple nuclei. It is an orbital that spans a molecule. So I've got this demonstration, the two different diagrams that depict our molecular orbitals. I'm going to kind of hybridize the two of them. I want us to imagine that a molecular orbital diagram has 3 lanes. On the far left lane, we look at a specific atom. On the far right lane, we look at a specific atom. I want to look at sp2 carbons in both of my lanes. In the middle lane, we look at what happens when those 2 atoms come together. So I'm going to show the double bond between 2 carbons. So I'm showing the the sp2 orbital that they have on the left and the sp2 orbital that they have on the right. Those are atomic orbitals. When those orbitals constructively interfere, it lowers their energy. But this has to be constructive interference. So those big lobes in the middle overlap with each other. Okay. When those big lobes in the middle overlap with each other, that should feel reminiscent of when we hybridized orbitals. We took different mathematical equations, we overlapped them, and we took the difference. Where they summed together, they got bigger. Where they subtracted, they got smaller. Why would that not still happen with these orbitals? They should still sum together into a new orbital. But instead of calling them a hybridized orbital, we call it a molecular orbital. So this spot in the middle where they're overlapped, we could just erase the overlap, and now we see it's one big orbital. And that's what you see on the bottom right. You see that one big orbital. I guess my shading is just flipped, but that's all. Oh, I think I flipped the shading because the black bled in with the black, so you couldn't see that they were actually just overlapped. They look like a big orbital. Where does the energy go? I'm taking orbitals of specific energy, and I'm getting something now of lower energy. Energy can't be created or destroyed. Instead of being released, it's transformed into a different orbital. So we create 2 orbitals in, 2 orbitals out. So rather than releasing this, what the atom does is it stabilizes one orbital and it destabilizes another. Instead of having them come together overlapped, it has them come together out of phase. Instead of in phase overlapped, they're out of phase overlapped. And when they come together out of phase, they subtract in the middle, they grow on the outside. It actually just looks like two orbitals pointing in different directions. But look at where the two nuclei are. One nucleus, another nucleus held within the orbital. One nucleus, another nucleus. They look like they're in different orbitals, but this is one mathematical equation. It's a very high energy mathematical equation. But here's the fun thing about quantum mechanics. Nothing has to occupy this for it to exist. If a tree falls in the forest, does it make a sound? I don't know, because I wasn't there. But if a tree fell in the forest, it would make a sound. Do electrons, sorry, I lost my track of my analogy. Electrons don't have to exist in this energy state for this energy state to be a plausible thing. So this would describe electrons if they were there. But electrons aren't going to go there because they're going to go to the lowest energy. Energy has been conserved by nature of it being possible. That's the thing. Now, actually, what Michael said is, yes, when the electrons actually drop down, they will give off some heat. That's why bond making is exothermic. But the energy of the mathematical orbital must be conserved as well, and it's conserved by nature of creating something that can exist of higher energy. Okay, up here, we're going to show our p orbitals. Now, p orbitals, because they are side to side, they don't get as much constructive or destructive overlap. So p orbitals aren't as energetically stabilized, nor are they as energetically destabilized. So p orbitals come down to some new energy, and they go up to some new energy. When they overlap constructively, we just get this big orbital that looks like a rainbow reflecting over a lake. Just two p orbitals squished together in the middle. When they come together destructively, it looks like two p orbitals, but just out of phase with each other. These are orbitals as much as any other orbital. An s orbital, as an sp2 orbital, a molecular orbital. The thing is, we don't refer to them with normal names. We refer to these molecular orbitals by the type of bond that they create. So, on the bottom, the overlap of hybridized orbitals creates what type of bond? So this is called a sigma orbital. Because if electrons occupy that orbital, they create a sigma bond. So it's a sigma orbital. The overlap of p orbitals creates what type of bond? So this is called a pi orbital. Beautiful. All right, I want to say we fill in some electrons. Let's say that each carbon brought one electron in each of its two orbitals. Actually, on the right-hand side, I'm going to draw my electrons upside down so that they can come together in pair. I've got 2 on the left, 2 on the right. When they come together in the middle, I've got a total of 4. First, they'll fill this low-energy sigma orbital. Then they'll fill this low-energy pi orbital. If electrons occupied the next highest orbital, there would not be constructive overlap. There would be destructive overlap, and it would exactly cancel out the energy gained, or the stability gained, from the p orbital. So we refer to these higher energy orbitals as anti-bonding. These are bonding orbitals, and these are anti-bonding orbitals. If electrons occupy these, they exactly cancel out the benefit of bonding. So instead of calling them pi and sigma, we'll call them pi star and sigma star. Those are their names. Sigma star is an anti-bonding orbital. If electrons occupy it, a sigma bond breaks.
So it's like a repulsive force.
Yeah, it is kind of a repulsive force. It's more like if electrons occupy this, then the energy of the system wouldn't realize that they were bonded anyways. Actually, I'll get to your question, Saray. A way that we can represent this is by looking at the theoretical molecule dihelium. Since helium only has the s orbital, we wouldn't have to consider the overlap of p's. And since helium has 2 valence electrons, there becomes a total of 4 valence electrons in the molecular orbital diagram. Congratulations, dihelium. Those heliums are bonded to each other. But they don't know it, because the energy of dihelium is equivalent to the energy of 2 helium atoms. If 2 helium atoms existed like this, it was probably just in transit. They probably came close enough for their orbitals to overlap, but that energy didn't ground them at all. It didn't stabilize them. They didn't know they were bonded in the first place, because the sum of sigma and sigma star is net zero, what you started with. So why do bonds not break? Because electrons make their way to lower energy orbitals. Valence bond theory will not predict that for you. Molecular orbital theory tells you why bonds break. There are 2 orbitals here that are called frontier orbitals. Those are the orbitals that have the highest energy electrons. So we call that the highest occupied molecular orbital, the HOMO. And the lowest, that's the most giggles I've ever gotten on that. The lowest unoccupied molecular orbitals, LUMOs. Those are the frontier orbitals, because it's always the highest energy electrons that are going to do something, or it's the lowest vacancy that's going to accept something. Things that are more stable will not be more reactive than things that are less stable. Things that are higher energy will do something first. If new electrons come in, they're going to go into a lower energy system. So in this diagram that I've shown, what is the HOMO MO? Which one? The HOMO is the highest occupied molecular orbital, pi orbital. It's either sigma or pi, but sigma's lower energy. Pi is a higher energy MO. It's the highest occupied MO. Which of my orbitals is the LUMO? Pi star is unoccupied. There's no electrons in it. Yep. And it's the lowest energy of all the orbitals that are unoccupied. So if new electrons are to come into this system, they will first break the pi bond. And that's a frontier orbital. If electrons are going to leave this system, they will come from the pi bond. That's a frontier orbital. If I gave you a Lewis structure and I said, what will break first? the pi bond or the sigma bond. Lewis structure would give you no explanation for that, though. But molecular orbital theory gave you all that confidence to say pi bond. The pi bond breaks first.
The pi bond is the highest occupied?
Yes, the p orbital is the HOMO, the pi star. The pi orbital is the HOMO, the pi star is the LUMO.
Is that because it's the least stable?
Yeah, exactly.
So would you say
It's the highest energy, least stable.
technically it might not have anything occupying it, but you would say the lowest unoccupied would break first and then the highest occupied?
There's two different ways that a bond can break. A bond can break because electrons leave that orbital, or a bond can break because new electrons enter its anti-bonding orbital. So there's two ways that a bond can break. New electrons are accepted into an anti-bonding, or electrons leave. And there are two reasons why this pi bond could break. What about a system that doesn't have a pi bond? Then sigma becomes HOMO and sigma star becomes LUMO. Elvira?
Is this only in this scenario, or is this always? Like,
What?
Is this the rules you're saying about like LUMO being pi star, and is that always true? Or
No,
just
because
carbon?
not every atom has a pi bond.
But if there is a pi bond, is that always true?
Yes.
Okay.
If there is a pi bond, then it's always true. If there's not a pi bond, then it shifts. Yeah.
Okay.
Gavin? You got a question? Oh, okay.
So you're saying that if an electron leaves the system, it's going to come from the pi bonds first, and if it enters, it's going to pi star?
If there is a pi bond. Correct.
Otherwise, it's going to go to the sigma.
And this will become a lot more relevant later in the semester when we start doing reactions with pi bonds. We'll understand, because of this, why it's the pi bonds doing it.
So I've read some papers and I've read in textbooks where it talks about, like, let's say electrons are excited and they go to the higher shell. Is that the anti-bonding?
Yep. Do you know oxygen has a really beautiful molecular orbital diagram? You guys might know molecular oxygen's Lewis structure, which looks like this. I think we can agree that that kind of looks like it has, it looks like it has 4 lone pairs. What it actually has is a sigma bond, and 2 pi bonds, and then half of an anti-pi bond. So there's what? 2, 4, 6, 8, 10, 12, 2, 4, 6, 8. I must be forgetting. I think there's like another one here. I don't know. I don't know what I'm doing wrong. Oh, maybe it's. No. Anyways, the idea is oxygen actually has unpaired electrons, which we call radicals. And that's why oxygen can be kind of reactive. It's actually why oxygen is magnetic as a liquid, because it has a magnetic moment from those unpaired electrons. It actually has 2 pi bonds and 1 anti-pi bond, which means in total it has just 1 pi bond. You wouldn't guess that from this. Oh, I think I remember what I did wrong. There's a non-bonding pair in the middle there somewhere. Okay, so here's the weird thing about oxygen. It doesn't have 4 lone pairs. It actually has something like 2 lone pairs, 2 pi bonds, and 1 anti-pi bond. Things you wouldn't expect looking at a Lewis structure that only a molecular orbital diagram could give you. Okay, I'm not going to test on MO that much, but I'm going to use it to explain things. So if you're struggling with MO, there are some problems that you can do on active. You can Google some things, but it's going to be very low level. We didn't get to the next worksheet that I had hoped to. If you would like to take this worksheet over the weekend, you could get a head start on doing bond line structures, but otherwise I'll bring these in on Tuesday, and we'll start transforming the way that we look at molecules and communicate about molecules. All right. Have a good weekend. I'll see you guys next week.